Okay, I want to make one point and then talk a bit about my research in relation to that point. And since this is a looking ahead symposium, I want to take the opportunity and look ahead a bit into the future. My point is that I believe that the question of whether the mind is computational will become, or at least should become, a non-issue. Truth be told, the whole debate is a little bit a child of the 90s. That was when the debates around the computational theory of the mind were hottest, and when I think a lot of misunderstandings were produced which still linger around the edges. Computation is a very abstract concept, and it's a very broad concept. In computer science, you basically define it as everything that a Turing machine can do. And a Turing machine is a really, really abstract thing. It's not something which anybody could ever use or build or so, because it has infinite resources. This is important because all the things around us that we do call computers are therefore fundamentally different from Turing machines. And they also display a lot of variety. The abstract concept of computation can be realized by very different architectures. It's just that one architecture has become so widespread for various historical reasons and perhaps functional reasons that this is what we think about when we think about computing. But all the things you can in principle do with a Turing machine, you can do, for instance, with certain kinds of neural networks. You can do them perhaps in the future with quantum computers. You can, in the very near future, probably do them with so-called Bayesian chips, which are now a very active area of research and industrial interests. So it is kind of important to separate these two issues, computation and computers, not conflate them. And once you do that, and you see how broad computation is, and how general the concept of computation fits to the idea of information processing, then there really is no alternative anymore to saying that part of what is happening in the brain is computational. But it's also not going to be very informative anymore. And this is something which is important. We should distinguish more clearly in cognitive science between how computation is implemented and how it is being used. Because the things I just mentioned, these various ways of realizing part of the things which a Turing machine can do, do not necessarily tell us anything about how computation is used in the brain. I mean, nowadays we have a pretty good idea of which computing machines are better analogs for computations in the brains than others. Of course, what is happening in the brain is better modeled by neural networks than, for instance, a more symbolic architecture or a classical computer with this kind of von Neumann architecture. And this is going to be an interesting and amazing field of research, but we should not have too high hopes that research that tells us more about how the brain actually computes allows us to understand the brain in some kind of algorithmic way. And that is due to a property which has been known since the beginning in research about neural networks, and that is, once you've set up such a thing, even a very simple neural network, it is very difficult for the human mind to understand it. It is very difficult to, as it were, reverse engineer. It's very difficult to figure out why it does certain things. Whereas the architecture of a typical personal computer is much more amenable to this kind of thinking. So although this will be an important question, I do not think that we should place too many hopes in seeing this as a key area for like understanding how the brain works. What is more important and what I think has generated a lot of interest in recent years and a lot of interesting results is research in how computation is used in the brain. And I just want to mention the paradigm of embodied and situated cognition here because it's very important for my own research and because I think it fits quite nicely to many of the things that Pete has said. In embodied cognition, you focus on computation not as something which happens within a machine, but which happens due to interactions between an entity and an environment. And the nice thing about it is that you often can see that computation is much easier once you view it in an embodied perspective. Take, for instance, the problem of a robot grasping a glass. Also, imagine that this is a glass which is like tricky, it can break, you have to be really careful when you grasp it. In order for a robot hand to figure out how to do this, it would have to either develop some kind of sophisticated representation of all the properties, measure exactly how it has to grip so in order not to break the glass. Or it could try to mimic how humans do it. And humans achieve this feat of grasping something by exploiting, for instance, the morphological properties of the human skin, which is soft, by exploiting the properties of tendons, which are flexible, so that in the act of grasping, you can be imprecise. You do not have to make precise computations. You can adapt because you get immediate feedback, because you also have sensors on your fingers. So more embodiment, less computation. Okay, let me draw the line here and briefly talk about how this is a paradigm which I use in my current research on pointing, which I've talked about a little bit in the previous symposium. So what I'm doing is I'm trying to build agents that can understand simple communicative acts such as pointing and a few other very simple kinds. And because I draw on this research on embodied cognition, for me it is important to conceptualize these agents as embodied, as something that actually has a body and acts within an environment. And yes, put it in some kind of realistic, more or less realistic social situation in which interaction takes place. And then the problem of comprehension of pointing has a lot of, or is receiving a lot of constraints which make it much easier than if you, for instance, tried to teach a disembodied entity, just a computer with a camera, to understand pointing. And I want to mention two ways here. First, the robot, or the virtual robot here, is located in an environment in which it not only interacts, but in which it already is able to act. So it can walk around, it can manipulate things. See here. This is real-time screenshots. So it can walk around, it can manipulate things, it can look at things from different perspectives. And with all these action abilities, it has a pool of things it can draw on when it tries to interact with the human, which is here represented by an avatar. Second, it is also embodied in the sense in that I give the agent the ability to perceive affordances, which is something we can perhaps talk about later. It is a very important paradigm in the field of embodied cognition, which states that perception is not just for information gathering, but it is for action. So when we see things in our world, we do not just see entities, we see action opportunities, we see graspability, we see drinkability, we see something we can walk on, something we can manipulate. And with these two kinds of embodied knowledge, so to speak, the problem of understanding pointing becomes one of understanding what kind of action the robot has to carry out on the objects, the affordances of which it already knows, in response to a pointing gesture. Okay, and let me close here and we can perhaps talk more about it in the discussion.